Okay, while Charlie's setting up, I'll introduce him. We're really pleased to have Charles Baily from the University of Colorado. Charlie is one of the key figures in the PhET program at the University of Colorado, which is the physics education center, which some of you I know are familiar with because of discussions I've had with you about it. Their online materials are, I think, famous across the country, and we were really eager to have him come, but we were told that unfortunately he was taking a faculty job in Europe in March, and maybe it would be very difficult to get him, but turns out it's later in March, so we are very lucky to have him with us. So I think we've almost timed it perfectly. Okay, I see these things set up. All right, great. Okay, Charlie, take it away.
I'm sorry. Can everyone hear me in the back? Speaking this? Great. Yeah, I am the last speaker of the day. I believe the conference is scheduled to end at 5:30. I hope when that time comes and I'm still talking that you're not running for the door. Before I get started, though, I wanted to poll everyone really quickly. How many people here, just raise your hand, please, are you aware of physics education research as a discipline within physics? Very good. And how many of you have actually tried to use techniques like interactive engagement in the classroom in PhET simulations? Okay, people are probably very excited about that. All right, so today I'd like to talk a little bit about active learning and try to spend maybe a little more time talking about quantum simulations in the classroom. Before I do, though, I would just like to give credit to my colleagues at the University of Colorado. I'm actually going to probably spend more time talking about what they do there than what I've actually done. But I want to make sure you understand this is a very large collaborative effort, and we're growing all the time. Okay, so how important is education? I'm not asking that to be facetious. I'm sure that probably everybody in this room, like myself, believes that education for its own sake is important. Though at the same time, that doesn't work so well in the real world. A lot of people are thinking about education in terms of return on investment. Some people are thinking about economic competitiveness, and some people are even thinking about national security. So as Newt Gingrich wrote to Congress in May 2005, he had been serving on a commission on national security for the 21st century, and he said, "The crisis in scientific research and education is the second greatest threat facing American national security. Only a nuclear or biological weapon released in an American city is a greater threat." Well, what did he mean by a crisis? I think this is very well illustrative of that. What we see is that this is 2006 PISA rankings, international rankings in science, and we see that the U.S., in terms of developed countries, they're ranking 21 out of 30 in science and 25 out of 30 in math. And if we fast forward just a few years later, the same study in 2009, you find that the ranking has dropped from 24 out of 30 in science and 31 out of 30 in math. I'm being a little flippant when I say that, but perhaps I shouldn't. This is actually quite serious, because although the raw scores for the United States did improve somewhat, as you can tell, we dropped in the rankings because the other developed nations, they were actually improving more than we were. But instead of just seeing this as a crisis, perhaps we should think of it more in terms of a challenge. So what's lying ahead? It's projected that there's going to be a need for over 1 million more science, technology, and engineering and mathematics graduates needed over the next decade. This is above and beyond the jobs that are currently out there for physicists and biologists and so forth. These are simply jobs where this kind of skills and knowledge that are associated with science, technology, engineering, and maths, or STEM, is associated. These new jobs are going to be created. And the Obama administration has also called for 100,000 more effective STEM educators in the next decade. And so in order to meet these goals just for the STEM grads, that means we're going to have to graduate on average 100,000 more STEM students per year over the next decade, relative to about 300,000 that we're graduating now. And indeed, the APS and the APT have made a call in 2007 for doubling the number of physics majors that are being graduated to address critical national needs, including K through 12 education, economic competitiveness, energy security, and an informed electorate. So how might this happen? Well, we've been working a little bit on this at the university level, of course. They say that these first 2 years are important. And what could be done at the high school level? Well, obviously better preparation. Sending the students our way with a greater understanding of physics and mathematics and so forth would be beneficial for us. But then also in terms of retention, and I say not this in terms of recruitment, but rather retention in the sense that what we find is that we actually do quite well in retaining students who show up at our doorstep already with positive attitudes about science or sophisticated views about the nature of science. We're actually going through a filtering process where we're losing the students who are coming to us without these kinds of attitudes and beliefs about science. And I would also say that some people are arguing that we are losing students because we are teaching them only about 19th century physics. And I would say, just from my own perspective, this is true for myself. I got very excited about physics when I was a senior in high school. And after my first year in college, I was about ready to switch majors because I really just couldn't get myself excited about blocks sliding down inclined planes. But then I took a quantum mechanics course, and that was when I really knew that this is what I was meant to do. I was hooked then, and I'm still hooked now. Okay, so in order to solve a problem, we first have to try and understand what exactly is the problem. And the problem is in the traditional, I'll call this the traditional model of education. And some people would label this as transmissionist in the sense that we have some kind of content, whether it be knowledge about circuits or something like that, and somehow or other the instructor is transmitting this information to the individual through words or actions and so forth. Bill Watterson has a nice little depiction of what this is actually like for students. But we received a wake-up call that this is really something that's not working, and it came in the form of the force concept inventory. It's a paper by Hess, News, Wells, Swackheimer. It appears in the Physics Teacher in 1992. And what this is it's a multiple choice survey, pre, post. We give it a pre-instruction and post-instruction so we can talk about what students came in knowing and then what it is that they left knowing and talk about the difference between those two. And this is something that even experts would agree that this is something they want their students to be able to understand. And in fact, we would call this a necessary but not sufficient indicator of conceptual understanding, because really what the force concept inventory does is it tests a student's understanding of Newton's 3 laws. Okay, and so this some people have been critical of it because it doesn't go beyond that, but I would say that if students aren't doing well understanding Newton's 3 laws, okay, then what is it that they're understanding beyond Chapter 4 in the textbook? Okay, so just to give you an idea of what kinds of questions are on here, right? It's a simple question, I would say, looking down on a track, flat on a table, a ball enters at point 1 and it exits at point 2. Which path does it follow, neglecting all friction? So A, B, C, D, or E. Well, obviously, we would like every student be choosing B, that it just moves off on straight. But I would ask, what does it mean when a student who's getting an A in my class is getting this wrong? All right, answering A or C or D. Okay, and I would argue this means that what we're doing, what we have been doing, is teaching students to be pluggers and chuggers, right? They're finding the right equation to use. They're sticking in the numbers that are going to get them the right answer, but they're not really understanding the concepts that are behind that. And so, as I say, a wake-up call came to us about a paper by Richard Hake. He surveyed a total of 6,000 students. This appeared in 1998. And what he did was compare learning gains. And so he defined this learning gain G as the post-test score minus the pre-test score divided by 100 minus the pretest score. So really what this is doing is that it's measuring what it is that the student has learned beyond what they already knew when they walked into the classroom. And what they found was that the students who were in what we would call a traditional course, simply a chalk and talk lecture, that they were generally scoring in this area about a learning gain of 0.25 or so. And what that would translate into is that students are basically learning less than 25% of the most basic concepts that they don't already know. And remember, this is focusing on really just Newton's 3 laws. And what we found then, what he also found was that if he looked at the same case with classes that were using interactive engagement, then we saw that the learning gains were much, much higher. And we've tried to reproduce this at the University of Colorado, and we've done it in 2 situations. One where we were using interactive engagement in the lecture hall, but then having traditional recitations, that would be a graduate student who is simply answering questions or doing homework problems at the chalkboard, and then replacing that traditional recitation with tutorials paired with interactive engagement, and we find that, again, we're getting very high learning gains. So it's a significant difference. So the question that I'm asking today is, can high school students learn more from interactive techniques adapted from university physics courses? We'd like to believe that I'm sure none of you are running the classroom this way, that students are sitting bored while you read to them some brilliant lecture that you've come up with. But rather, we'd like the classroom to look more like this, that students are talking to each other. They're articulating their knowledge, and they're defending their beliefs against alternative conceptions. I would argue that this is a valuable skill that students need to learn, the scientific argumentation. You don't learn this without practice, and it's better that students are learning it in the classroom in this low-stakes environment than some high-stakes environment, say, when they're at their first job. So today, I would like to talk just for a little bit about transforming the classroom using concept tests or peer instruction in the classroom, and also maybe the effects of using in-class activities or tutorials where students are working together. It means giving up some control in the classroom, but I think that the benefits from it are really worth it. And then I'd like to go on and talk about some of the PhET simulations, Physics Education Technology Project. I think that many of you are aware of them. But I want to talk about them in the context of modern physics courses, the quantum simulations. I'm going to talk about the laser sim. This is my favorite PhET sim of them all. And then also about matter waves. And if there's time permitting, talking about the effect of talking or not talking about the interpretation of quantum mechanics in the classroom. It turns out that this actually has a very significant effect on student thinking. And I'll tell you more about that if we can. So there have been many PER curricular innovations, and I would say just as to get started, a person can't go wrong by just picking up Eric Mazur's book, Peer Instruction, or Joe Reddish's book, Teaching with the Physics Suite. But there can be really quite a bit out there there can be so much that a person really doesn't even know where to begin. And so one website that I'd like to point you to is the PER Users Guide. It's at just perusersguide.org. I'll have all these URLs on a final slide. But a person can search through here, and you can find what types of teaching techniques are supported by research. You can search by methods and course levels and so forth. And so this is not just for university instructors, but really high school teachers or anybody. They can all find some kind of benefit from this. And to talk about the concept tests, just to give a specific example from modern physics, we consider this glass tube. It's full of atoms. It's like a discharge lamp. And these large atoms, these are atoms that are in an excited state. The ones that are gray here, they are in the ground state. And we send in 3 photons. And we might ask the students, what would you expect that on average? Would you expect that more photons would come out the right end of the tube, less come out at the right, the same numbers go in, or none will come out? Well, in this case here, we'd find that just about half of the students, when we gave this concept test in our class, were choosing the correct answer, which that on average, that's a very important caveat, that less will come out on the right-hand side than went in. But the important thing is not that the students are getting all getting the correct answer. What's important is the conversation that went in first amongst the students themselves as they were deciding upon an answer, and then afterwards. So as an instructor, an important thing is that we listen to the students' ideas, and we don't simply tell them what the correct answer is, but we elicit students' ideas, we get other students to respond to that, and to make their arguments as to why it is they answered in the way that they did. Now, there are some arguments against using these concept tests, and one of them being that it eats up time. Well, that's true, but important ideas can be complex, and sometimes it's really worth taking that time to talk about these things. And I would say, just in the same spirit as this forced concept inventory, right? If they're not getting these most basic concepts, then really, what is it that they can understand beyond that that are more sophisticated ideas? So it's very important, I think, as an instructor to find out where it is that your students are at any given moment during a class period. Some might think that discussion's easy in small classes, and so I don't really need to test my students like this. But the truth of the matter is that we, the instructors, and they, the students, don't always know that they need to ask a question until they've been given an opportunity to apply new information. Now, if that doesn't happen until they go home and if they're hopefully doing their homework, well, that's long after they've had really an opportunity to be asking you in class. So some of the benefit from these concept tests is for students to really test their understanding and find out for themselves whether they understand what you're talking about before you move on. Students may be resistant to it. Yes, it's true, and we find that even at the university level, because in some ways what we're doing is we're telling them this is a new kind of learning. What it is that you've been doing before that was successful or made you successful in school is not the kind of learning that we're trying to encourage. Okay, and what we found that actually once the students get into the habit of it, this becomes a classroom norm for them, then they become much less resistant. In fact, what we find is that they become really enthusiastic about this kind of teaching. And some would say that it takes some extra effort for teachers, and it's true. It does actually take more time to come up with good concept tests than it does simply to write a lecture. But luckily, we don't have to all reinvent the wheel ourselves. We have question banks that are available if you want to try this out. And again, I'll point you to some websites where these are available at the end of the talk. Moving on to talking about in-class activities. This actually started out with the University of Washington, the tutorials in introductory physics. And what this did was really reconceptualize what it is that students are doing in the classroom. It's a combination of many factors here. So it would be the materials that are being provided, but it's also a change in the format of the classroom and how it is that instructors are interacting with the students and also how the students are interacting with each other. And finally, as I say, it's not a case where you want to simply be telling students the correct answers when they ask you a question, but rather you want to help them build their own understanding. It's a very different kind of instructional role as a teacher. Just to talk about these specifically for the tutorial materials from the University of Washington, these aren't just for university students because really the focus is on conceptual understanding. And so there isn't any higher level mathematics or calculus in this case here. But if you are looking for other kinds of materials or ideas for activities, things that students can be doing in the classroom, one place that I would point you to is compadre.org. This is a place where a lot of people have simply they've uploaded their activities, their ideas, their papers on education and so forth. And even better, we have the quantum exchange. Okay, so beyond just the introductory level, we have people who are sharing with us their resources that have to do with modern physics and quantum mechanics. And actually, wow, CUBE is University of St. Andrews, where I am going in just a few weeks. They have developed a number of quantum visualizations, simulations, and so forth. Those I would say would probably be a little bit more advanced than maybe what the high school students are going to be used to. But one thing I would say that you can see in those is for example, the example that John was giving about the standing waves on a drum or something like that, where they have some nice visualizations so that people can see that. So how does this look different? How do our recitations, or how does just a regular old classroom look different in this kind of situation? You can see here what we'd have would be these students who all have their attention facing forward towards the instructor. And really, there's not really any kind of student-student interaction. It might be some student-teacher interaction, but really, this actually very much limits what's possible in the classroom to talk about or to do. And what we'd like to see instead is something like this. And you might be maybe limited by the infrastructure in your classroom, but if you can manage to create a situation where the students can be facing each other, talking to each other, and working on these problems together, then you have your instructor here. You can move from group to group and see how students are doing, help them along if they get stuck and so forth. But most of the learning is coming from students talking to each other. Now, some people feel like this might hinder students who are more advanced, and I would argue that actually they are benefiting just as much from these student-student explanations as this lower-performing students. First of all, these other students are getting an explanation from a peer, somebody who's using the same kind of language as them and understands maybe better where they're coming from as an instructor. But then also the advanced students are benefiting from it too. I think that we all know as teachers that you'll never understand anything so well as when you can explain it to somebody else. And this is what it is that these students are practicing. This is just a picture of this going on at the University of Colorado. One thing that I would suggest using is these whiteboards. It's a really great way for students to sort of play around, share their ideas, work together as they're doing this. And to talk about the effect of this, what we find, so this is the impact on different pretest populations. So these are the students, the low starters, as we would say. They came into our classroom scoring on this FCI pretest less than 12.5%. And what we found is that in the traditional classroom, we had learning gains about 25%, just what we had seen in the other cases. But then in the case where we had tutorials, that they were actually scoring learning gains that were upwards to to the 50% range. So this is the percent of students in the class that were in this population of 12.5%. So roughly a quarter of the students were what we would call low starters. And then we can also look at the high starters, ones that came in with pretests that were higher than 50%. Unfortunately, this represented only about 14% of the students that came in. But we found that, again, that also they are learning much more than they could be learning, at least conceptual, in terms of conceptual understanding. And we can certainly give them hard enough homeworks if we want to, really have them focusing on the math. And just to talk briefly also, that there are really long-term impacts. This is an interesting study that was done by one of my colleagues, Steve Pollack. He was looking at upper division physics majors, and he was comparing scores on the BEMA. This is the Brief Electricity and Magnetism Assessment, roughly equivalent to the FCI, but just about electricity and magnetism. And he was looking at students in two situations here. One where they had no tutorials when they were taking introductory physics approximately 2 years prior, when they were first learning E&M in the university setting. And we compare them with the students who had used tutorials in their introductory E&M 2 years prior. Okay, so we can see that there was really a significant gain or difference in how it is that these students were performing on this BEMA exam much later. And it also had a very significant impact on their course grades. We see that the ones who had the tutorials 2 years earlier were doing much better in the classroom. These are traditional classrooms that hadn't been changed in any way. It's, usual chalk and talk lectures. And they were doing better. So they had that basis, that foundation that really saw them further in terms of understanding physics and learning more and more physics. So if there's one thing that summarizes what it is that I'm trying to tell you, it's that it's not about our teaching. It's not about coming up with the perfect way to explain something to somebody so that they're just going to magically understand it. Rather, it's about creating environments that support the student learning, where students are building their own understanding, because really that's how it is that learning takes place. And one of the ways that you can do this is through these wonderful PhET simulations. And I tell you, if you don't know about these and decide to use them, it will absolutely transform your teaching, transform your classroom. find that these are really wonderfully popular with students, and they get to play around with them, and they learn a lot about physics. And in particular, we do have a number of sims that are related to quantum phenomena. It might be the photoelectric effects, lasers. This is one I want to talk about in just a moment. But you'll notice here that we've also expanded lately beyond physics into biology, chemistry, earth science, and math, and that we actually have resources for teachers. These are activities, suggestions, different kinds of problems or ideas about how it is you could run a classroom using these kinds of simulations in your teaching. And so now I want to tell you about this laser sim. I actually really found this to be quite incredible for my own understanding. I'd have to say, when I was a student, I understood all these things about spontaneous and stimulated emission and Einstein's A and B coefficients, but I really couldn't put it all together. Until I looked at this sim and played around with it. And even today, I still like to play around with it, probably much more than I should. So let's just let me show you what it is that you can see here. So I'm just we're sending in some photons here that are exactly matching the energy difference between, say, the ground state and the first excited state here. And what we see is happening right now, the lifetime of this state is short enough that really all that we're seeing here is spontaneous emission. The atom gets excited by a photon, and then it de-excites on its own, and it sends off that photon, it radiates it off in just some random direction. But one of the wonderful things about the simulation is that I can come in here and I can change up the lifetime of this, or I could just send in more photons. And what we would find is that we would see some cases of some stimulated emission, just like that. So what happens is that the atom is already in the excited state, and then a second photon comes along, one that matches that same energy difference. And what happens is that what we'll see is that two photons get emitted. This is a stimulated emission, and these have the characteristics of laser light. They're going to have the same energy, they're going to have the same direction, and they're going to have the same phase. Okay, so we can actually just without even talking about maybe the complex quantum ideas behind why it is that this has to happen, we can just demonstrate this as a phenomenon that can be harnessed in order to create these kinds of lasers. So let me, every time I touch the... Seem to have frozen the computer. At the very least, we can go over here. I'm not sure what's... Let me disconnect that for now, see what happens. But, so what will we do here? So what we can do is that right now we just have this glass tube with a single atom in here. And let me send in quite a bunch of photons. And then I'm going to enable the mirrors on the side. And we can start to see what it is that's happening when we want to create a Lay's effect. Okay, we see that there are some photons that are emitted spontaneously that are moving exactly perpendicular to the mirrors at the end. Okay, and so we get this effect that these photons are bouncing back and forth, and anytime this atom's in the excited state, if we were to somehow or other pump it to an excited state by some other means, then we could stimulate the emission of more photons that are going to be traveling in the same direction with the same phase and the same energy. So what would happen if we had multiple atoms? So let me enable the mirrors over here. And notice that we can change a lot of the different parameters. We can actually change the energy of the different levels. We can change the reflectivity of the mirrors and so forth. But let me turn on this lamp. This lamp is emitting, let's put this as photons so we can see this immediately. So you can see that there are photons that are being emitted by this lamp that are pumping it up to the third energy level. Let me just get rid of that. And then what we're looking for is we want to see some spontaneously emitted photon that's going to happen to be traveling exactly perpendicular to the mirrors. Let me turn up the amp control here, and I'll turn down the lifetime of the upper state. And this is something that students can explore, actually, why it is that it's beneficial. And so you can see what's happening is that more and more, so the atoms keep getting excited by this pump lamp. This lamp is pumping them to the higher state, and then we just get more and more stimulated emission photons from stimulated emission as they bounce back and forth between the mirrors. And now that we've built up some power here, we can actually turn down the reflectivity, and we can see that we're emitting photons. And in fact, I can turn down if I want to just have a massive beam come out there, and then we can see that it's exhausting the energy. And these are still getting excited by the pump lamp, but we don't have the reflectivity in the mirror, so we can turn this back up again. And you can watch the whole process go on and on. And in fact, you can also show here a wave view. What we'd find is that this cavity length is such that we can get exactly a standing wave that's forming in here, just from a classical perspective. And again, turn down this reflectivity and see the laser fire. Okay. So, seem to have killed my other presentation, but fortunately it's on this other computer. Okay. So, there we go. So we actually, we had our own crisis in education at the University of Colorado in our modern physics course, the one that we were offering for engineers. This is not even the one for physics majors, but we were just asking them the simple question before they came in, you know, I think quantum mechanics is an interesting subject. Would they agree? Do they feel neutral about that statement, or would they disagree? And we found that coming into the classroom, it's not displaying the numbers here, but this is it's coming in. The average was around 75-80% of students, which I think is fairly high, considering that they haven't chosen physics as a major, but then they don't even maybe know very much about quantum mechanics. But what we were finding is that after they were taking our modern physics course, is that yes. Sadly, and this is actually the average over a total of about 6 semesters, and so I can promise you that actually there were several semesters when this was much worse. But the end result is that students were coming out of the classroom, and after having learned about quantum mechanics and modern physics and so forth, that they were finding it to be not very interesting. And so this was some work that I did for my PhD dissertation, was to try and improve the situation. And what part of the work that I did was to develop, I would say, a new modern physics curriculum. And the idea was that we would expose students to the ideas about interpretive themes from the historical development of quantum mechanics. So beyond talking about complementarity and wave-particle duality and maybe even wave function collapse, which might find its way in there, we were trying to teach students about entanglement and non-locality. And we were doing this in a way we were trying to incorporate, for the most, as much as we could, just 2-level systems. Because really all of the quantum strangeness, everything that makes quantum mechanics strange and beautiful and wonderful, can be expressed in terms of these 2-level systems, whether it just be spin-up, spin-down atoms, for example. We didn't have to talk about it in terms of a Schrodinger equation or solving differential equations, these kinds of things. Really, we weren't using any more mathematics than simple probability and a few trigonometric functions. And so I would argue that this is something that could be entirely appropriate for a high school classroom, something that students could really get interested in to talk about. And what we wanted to do is also not simply to have them just accept our word for how these things are in quantum mechanics, or basically being the voice of authority. We wanted to show them experimental results on the foundations of quantum mechanics. So this would be talking about single quanta experiments with just single photons or single electrons, and then also distant correlated measurements in order to demonstrate this entanglement and what this is all about. And to introduce contemporary topics in quantum information theory, whether that be quantum computing, cryptography, and so forth. And really, I think the overall message is that this is a way for students to learn about exciting developments in experimental science. And this is not really a question of philosophy anymore. I'd say perhaps, for between 1930s and 1960s, probably people felt that wave-particle duality was the key feature of quantum mechanics that made it different from classical physics. But I would say, and it seems that some people haven't quite gotten the message, is that in the 1960s there's what I would call a second quantum revolution, where really now that we understand that we can apply a single wave function to describe single particle systems, single photons. In fact, as was mentioned earlier, that's what the Nobel Prize was given for in this last year. Our ability to manipulate these kinds of systems has really changed our perspective on the interpretation, the physical interpretation of quantum mechanics. And after implementing, I'll just mention that we do have all these course materials available on a website. Again, I'll give you that URL at the end slide. But we try to have as much information as possible for you to tell you about why we made these changes, how they're different. The original course materials were based on a project that was started by Carl Wyman. And, Carl liked to talk about BEC and that kind of thing. But this edition, this talk about interpretation in physics, in quantum physics, that's a little bit more of my work. But you can get all the materials that are in there. We have links to all the different kinds of quantum sims that were used in that classroom. And you can get all the lecture slides or the concept tests, those kinds of things, without any problems. And then if you're interested in having the homework and exams and the solutions that go with that, well, then you can just send me an email, and I'd be happy to give you the password for this website. And this was the result. So I really thought this was fantastic. We had a response rate of over 90% of the students, and we had, one student who felt sort of neutral about it. There wasn't a single student, though, who disagreed with this idea that quantum mechanics is an interesting subject. And we had 98% agreement, of students at the end of our course. And so I think this in itself really should be enough motivation to suggest trying to make these kinds of changes in your own courses. And one of the ways that we can talk about this, I think this is a really wonderful experiment, the double-slit experiment. We can do this experiment with photons or with electrons. And one way we would describe it, looking down on this double-slit system, we would say a plane wave, which is representing the photons or electrons. It's incident on this double slit. And each of the slits acts as a source, a wave source. They spread out behind each of the slits. And in the regions where they overlap, we have the interference, and they can constructively interfere or destructively interfere with each other. And what we end up seeing then is this fringe pattern on the detecting screen. In the places where we have constructive interference, then we have these bright fringes, and where we have destructive interference, these dark fringes. Well, the interesting thing is that you can actually do this experiment not with just a beam of light or a strong beam of electrons, but really single electrons, one at a time. We tried telling students about this originally in the classes, and I think they were really quite skeptical that this might be possible, that you could really just send through one electron at a time. Well, here it is. It's actually been done. This was done in 1989. If you go to the Hitachi website, you can actually find these kinds of movies and download them and show them to the students. But there can be no denying that these are electrons that are being sent through what's essentially a double-slit system, and they are striking this detector one at a time. And so it can't be that what we find then, as we let this run on, is that eventually we'd see the same kind of interference pattern. So each electron comes in, and it strikes the detecting screen at one single point in space. This is what we'd say is the particle-like property. But over time, what we'd find is that statistically we see the same kind of interference pattern as being developed. And so we'd say if we're really just sending in one electron at a time, then it can't be that these electrons are interfering with themselves, that they have these wave-like properties that interfere with themselves, but that really a proper interpretation is that each electron must be interfering with itself. And we can show this in the, this is the quantum wave interference sim. And I'm not going to run the risk of freezing up the computer after this one. But basically, it's very much like this. What you would see in this case here is we have an electron gun in a double-slit system. And what you'll see here is the probability density for this, just a single electron that's being sent through. And this wave, probability density, passes through both slits, and then what we see is a plink. We just see a single electron right there that shows up on the screen. And if you let the simulation run long enough, you would be able to see the same kind of interference pattern build up. And you can play with various parameters, such as moving the screens around, reducing the distance between the slits or the width of the slits. But what I think is really interesting is to ask ourselves, what is this really showing? What is it that students would see in this case? And to talk about these interpretations, one of the ways that we can cast this in terms of what I would call a realist perspective, and it would say that each electron is a tiny particle that went through one slit or the other, and we simply can't know which slit that it went through because any attempt to observe that would disrupt this interference pattern. And then what I'll call a matter wave perspective is exactly what I had said before. The interpretation, which I think is almost unavoidable when we think about just a single electron going through at a time, is that each electron went through both slits and interfered with itself. And then what I would call, say, an agnostic perspective would say that we can't say what the electron's doing between being emitted and being detected. And in fact, this is a very popular view, the Copenhagen interpretation. This is what Niels Bohr would say, that it's really not a statement for science to make. If things that can't be observed, we shouldn't be talking about that. We should only talk about measurable quantities. But as I say, I think that's people who are still subscribing to this. I think the Copenhagen interpretation is really falling out of favor amongst practicing physicists. And there's actually a very noticeable impact on students when you take sort of this agnostic stance to say, well, we can't really know. In my mind, it's not really any different than saying the students, nobody understands quantum mechanics. And this is something that I would never say to students. Perhaps we don't understand what it is that quantum mechanics is telling us about the true nature of reality, but it is an understandable theory. There are models that we can use to see as in order to make the physical laws self-consistent, ways that we can have of understanding what it is that's going on. And to deny students that tool, this visualization, I think is really taking away a valuable tool that many physicists are using and feel very good about. So what are the effects of the different ways that instructors talk about interpretation in a course? So up here, what I'm showing you, these are the student responses, the realist, agnostic, or matter wave, as I just described them on the previous slide. And then what I'm showing you here is actually we can use the same kind of categories to talk about the instructional approach that teachers are taking. So in one particular course, where what I'll call it's the same engineering course, but the instructor was using what I would say would be a realist or a statistical interpretation of quantum mechanics. What we found is that the majority of students were really feeling quite confident about this idea that it must be that each electron, being a localized particle, it can only pass through one slit or the other. And we had another course where the instructor was using this matter wave interpretation. So in this one particular context, this instructor was explicitly telling students about this idea of the electron passing through both slits and about how this explains the interference pattern and so forth. And so we can see that the students favored this interpretation quite strongly. And then these, just for comparison, these were engineering students, but these are physics majors who were taking a similar class, but one that's specifically designed for them, where the instructor is taking what I would call the Copenhagen or agnostic perspective. Really, it might be embodied in that popular phrase, shut up and calculate. Right? I mean, some instructors feel very uncomfortable trying to answer these questions, and in fact, many physicists do as well. And in the end, for a lot of them, it doesn't really impact or influence the kind of work that they're doing. And so, in the end, let's stop worrying about what it is that's going on. Let's just keep getting the right answers by applying the equations correctly. And this was this course that I was telling you about, the change where we have included these interpretive themes. And it's not so different from the matter wave course, but we did significantly reduce the number of students who were taking this realist perspective on this double-slit experiment. And I would say that this agnostic perspective is not necessarily unsophisticated. for the students. It might say, well, in the end, maybe I don't know, or I don't have enough information, and so forth. And so they don't want to take just a particular stance. They just want to say, well, for me, it's still an open question. But what's interesting is that if we compare this to a different context, so when not being observed, an electron in an atom exists at a definite but unknown position at each moment in time. So this was, again, something that came up earlier, this idea of a localized electron that's whirling around the nucleus like a planetary system. It just really doesn't work when it comes down to what we know about how it is that charged particles behave when they're accelerating. Well, in this case here, these students all really were happy to agree with this statement. And I would say beyond just what the instructor was telling them, that this is really their intuitive view and perhaps what they might come out of high school still thinking about, because they maybe stop at the Bohr model, where they are taught that the electrons are going around in circular orbits. But what I think is interesting is that in this matter wave course, so this was the case where the instructor was explicitly telling students about what it is that they should be thinking in a double-slit experiment, but then talking about uncertainty and the wave-particle duality and so forth. It didn't translate over to a context where he didn't explicitly talk about it in the same way. So many instructors feel that I'm going to talk about the difference between classical and quantum physics at the beginning of the class, and then let's get on with the business of learning about quantum mechanics. And it turns out that if you're not talking about it in a variety of contexts, that students aren't just naturally transferring that over to these different contexts, or really just having a wholesale change in terms of how it is that they think about quantum entities. And for comparison, we have our class of physics majors who were taught by the Copenhagen agnostic instructor. And again, I would still call this an unfavorable view. And so not perfect in our interpretation class of the engineers, but I would say it's definitely an improvement. This is my favorite graph. It's very nice and pretty, the way we go across here. The realist interpretations versus matter wave, or even agnostic interpretations. And whether or not this idea of locality and so forth is something that every instructor is going to think is important, I certainly would hope that all of us would want our students to disagree with this idea that the probabilistic nature of quantum mechanics is mostly due to the limitations of our measurement instruments. Okay, this is not this uncertainty in quantum mechanics. It's fundamental. It's different from classical ignorance, where perhaps the electron might be whizzing around the atom in a probability cloud, and it's simply chaotic motion, and we can't predict ahead of time where it might be found. And in this case here, we see similar kinds of effects. And again, though, I'm not surprised that the physics students or the physics majors are not agreeing with this. I would expect them to have a little more sophisticated views about this, even if the instructor is not taking that particular point of view. And just to show you here that there was a correlation in terms of student interest in the subject and the particular approach that this instructor was taking. And this is for example classes, but I've seen this again and again because I've studied this for several years, actually. And so you can see that really getting these engineering students to really think that quantum mechanics is as interesting as physics majors are. Okay, I think that really in itself is a tremendous accomplishment. So just to wrap, I understand that I'm running short on time here, and so just to wrap things up, I'm going to tell you that I'll be happy to answer your questions, but we have much more information. I'll leave the slide up for people, and if you're not taking notes, I do always post my slides on my personal web page, and I think that link is listed in the participants section. But if you're interested in concept tests and so forth, both for the introductory level and beyond, so a bunch of these start with per.colorado.edu/CTS. That would be for the concept tests and so forth. And for the course materials that I was describing for you, that would be the same. Start with /modern physics. If you're interested about using clickers in the classroom, or let's not get caught up in the technology, you can get the same effect by having students holding up colored index cards and writing the questions on the board and so forth. But if you want to look at some videos that talk about different styles, techniques of using clickers in the classroom or concept tests, these are available at the STEM clickers. The quantum, all the PhET simulations, whether it be classical physics and beyond, biology, chemistry, and so forth, is available at phet.colorado.edu. I mentioned before the PER User's Guide. That's a place where a person can go try and filter through this really plethora of information that's out there. Compadre.org, and then /quantum on top of that. That takes you to the quantum exchange. And just to mention, I really don't know of many quantum simulations out there, but another good place to look is Falstad. Shows a lot of these, for example, atomic orbitals, the drums vibrating, that kind of thing. Thank you very much.
Before we go to the questions, I just want to point out that all of the talks are recorded, and you can navigate there at kitp.ucsb.edu. All right. First question here.
So you started by showing how the U.S. was not doing well in these rankings, and then you talked about how to improve education here, but you didn't go back and connect to whether these improvements will actually ever change those rankings, or more importantly, if you think we're not being competitive, do you think the ones doing better, quote unquote, have lessons to teach us?
Well, I would say that there might be some things that are specific to America that perhaps are never going to change. And that might be, for example, paying teachers well, attracting really the best minds to become teachers, and really valuing teachers in America. But what I would really try to say that would be important is what we found is that students that come to college showing up with positive attitudes about science and about the nature of science, and really being excited about science, that these are students that we tend to keep. It has less to do with their mathematical ability, their actual knowledge, but rather having these ideas that science is something that could interest them and excite them, that they would like to continue and do as a career. And so I think that if we can start early in that case, if we can get students excited about physics, which might include, for example, changing the learning experience, instead of writing equations on the board, getting them actively involved, using these simulations and so forth, getting them excited about science and learning these very important concepts before they show up at the university. I think that this could have a very strong impact. And we want to remember that we're not just training the next generation of scientists, we're also training the next generation of teachers of scientists, future scientists, and so forth. This is the way that our society reproduces itself. And so I feel like this effect can propagate on down the line.
Is there a timeline on when all the PhET simulations will be converted to HTML5 or have that option?
That is in the works. So they have not actually started in on the new coding, but they are right now exploring everything that they need to know in order to make a complete transition over to HTML5, so that all these simulations can be used on a tablet, phone, that kind of thing. Yeah, that's definitely that's really the major project that they're thinking about right now. And it's in the works. I can't say when it's going to be done, but it's something that you can look for.
Are there other questions? Yes.
This isn't really a question. I just want to say thanks. The PhET simulations I've used for years, and they're amazing.
Yeah.
So.
No, I'll be happy to share with all the developers the positive comments that I've heard from everybody here at this conference. Thanks for saying that.
If there are no other questions, I'm going to adjourn the entire conference and send you back to wherever you're coming from. Oh, yes, the surveys. There's a little box on the desk outside to put your survey forms in. Please don't forget to do that.